This video is the second part of the tutorial series for the bending of cylindrical cell, which is inflated by air. So I have prepared the model in the previous video. So let's look at a little bit what we have done in the previous video. I have just uh, created a load which is parallel to the top face in the previous video, and I've given a load magnitude 500,000 Pascal. So this is the load, and we had submitted the analysis. Analysis is completed. So now click on results to get into visualization module, and we have this. So now click on this plot contour on deform shape. So click on this. Now look at this. Now it is showing the deformed shape, and so this is the results. Let's increase these fonts a little bit. So go to viewport and viewport and notions, state block, set font. Just increase the font. I use these settings many times, so this now it is visible a little bit. So now the variables or field variables or field output you can select from here. It is stress, this is displacement. Now we have selected stress and just showing one Mises stresses here. So just look at this. Let's see how it has evolved. Click on this. So it is showing okay, now it is the front view, I think. Okay, I just wanted to show in YZ plane because my load is acting in positive Z direction, so it will show a tilt bending of the cylinder. By clicking on this, it is showing the result at load increasing. So as step time increases, load increases. I have defined amplitude. Let's look at a little bit back in its step 2, amplitude, manager, and edit. I have defined this amplitude and used it in load. If you remember, if you go through the previous video, I have selected this amplitude along with the load. So load varies with time linearly. So as time goes to 0 to 1, load amplitude goes to 0 to 1. So the load get multiplied by these factors. So basically this is varying linearly with the time. So again go to the visualization. So as this step time increases, load also increases. So basically when it is 0.4, so we can say that we have applied 500,000 Pascal load. That means, so we can say that now this result is shown for the load that 500 kilopascal times 0.4. Okay, so this is how we calculate the load at some middle time step. So at this time step, load is 0.4 times 500 kilopascal. So I will increase. Look at this. This is tilting. Okay. Okay. Great. This is. Look at this. So in this analysis, I am using PVC material, and for PVC material, the critical, the ultimate strength for PVC is around 50 to 60 megapascal. Okay, so let's set this limit here to plot the results so that we can see where the maximum stresses has gone above the ultimate strength, so the material fails at that stress. So go to option and click on contour and limits, and then specify your limits. Let's say 55 megapascal. So I have applied. So now results are shown. The color has been adjusted as if the maximum load, uh, these gray areas are above, beyond 5.55 megapascal. So these are the reasons where stress has gone above uh, the ultimate strength, that is 55 megapascal. So these are the failure reasons. So we can spot where it fails, at what load it fails. So let's go back and see. Not now. Here you can see this is a gray reason. So the first gray reason appears here. So at around zero point 0.4 times 500 kilopascal. So basically around that load, the material fails. The material of the cell structure, that means PVC fails here point. So this is how we interpret results and see the bending at what load it sustain or it fails.